Hello, I'm Pasquale Gallo, postdoc at Alta University. My talk will focus on the evaluation of the fracture toughness at small scale by using the theory of critical distances. First, I'm going to show you a brief introduction and motivation of this work. After that, we're going to see the experimental characterization of single crystal silicon fracture toughness, and then a synthesis by using the theory of critical distances. Later, we're going to see the results and then the conclusions. Miniaturization of electronic devices has pushed the size of components to smaller and smaller scale. Even at these small scales, we still have failure because of crack initiation and propagation. Material behavior at the micro and nanoscale has been brought into the domain of fracture mechanics. So investigation of linear elastic fracture mechanics at the micro and nanoscale is nowadays fundamental for small scales. It gives a direct impact on the design and static fatigue assessment of micron and nano electromechanical system. But on the other hand, it gives also impact on the macro scale as well. Indeed, phenomena usually considered at the macro scale are being analyzed in more and more details in smaller and smaller scales. Let's think, for example, to the micromechanism of fatigue or the fracture. So the fracture nanomechanics enables a new path and new methodology to explain and investigate the macro scale phenomenon as well. Indeed, we can, for example, isolate and investigate mechanisms without influence of secondary factors. Imagine, for example, effect of microstructure. We go from a kind of average mitigated observation to pure observation. So the silicon is the most common material used in electronic equipment. It represents an ideal brittle fracture, and the crack propagates by atomic bond breaking. We have several experimental challenges when dealing with very small scales. Let me underline two when we deal especially with the single crystal silicon. First, we need an atomically sharp crack to obtain a reliable value of the fracture toughness. And the second, with the focused ion beam processing system, for example, we can provide an accurate control of the geometry, and we can realize an atomically sharp crack directly with FIB. As an example, here you can see a study of the same experimental test we are going to see in this presentation, but by using a finite fracture mechanics approach. As you can see, if we have a nanometer size small radii at the crack tip, sample behaves as a notch, and we may conclude that the fracture toughness is scale dependent and increasing actually. The smaller the scale and more brittle the material, the more we need to pay attention to this effect. Given the introduction before, these are my research questions. Is there a simple tool to evaluate the fracture toughness by employing notch sample of different geometries? And if this tool exists, does it work and why? I try to find my answer in the theory of critical distances, as I'm going to show you very soon. The theory of critical distances in the form of the point method says that failure occurs when the linear elastic maximum principal stress at a given distance from the notch root equals the inherent material strength of the material. This critical distance is related to the fracture toughness, as we can see in this slide. Therefore, we can express the fracture toughness as a function of L and the inherent material strength. The point is how to find these two parameters. Well, the failure condition is valid for any geometry, regardless of the notch. Therefore, we can just overlap in a single graph the linear elastic stress field of at least two notches of different sharpness at incipient failure, and the intersection point would give us both these quantities. And that is exactly what we did with the experiments I'm going to show you next. So we realized four notch nanocantilever beams made of single crystal silicon. We realized them by the focused ion beam processing system. Just a few words on the silicon. We know it is an orthotropic brittle material. It has a face-centered diamond cubic structure, and you can see the material constant in this slide. How to realize those samples is shown here in current slide. It is a very time-consuming process, but anyway, this is faster than realize the pre-cracked samples. So we first extract a big block from the silicon plate, and later we transfer this block on a tip of wire, and we work it with FIB. As I said, we can try to control the general geometry, but when it comes to the notch, we can just try to do our best. So we cannot have a precise control on the notch root or on the crack tip if we want to realize a crack. So here you can see the geometric detail. These are measured at the best of our capabilities by using CEM pictures. When samples are ready, the experiments are conducted using a sample holder with a loading device in TEM with a digital camera and therefore under vacuum. Loading device consists of a stage that can move in 3 dimensions and has a diamond tip driven by piezoelectric actuator. The load is simply applied to the specimen by pushing it into the wedge-shaped diamond indenter. The load is measured by a sensor beneath the indenter, while the displacement is obtained from the videos. Here you can see an example of the experimental test. As you can see, we're pushing the sample towards the indenter until we reach our failure. Here we see the results. So when we realized all our experimental tests, we reanalyzed the stress distribution at the critical load by using FEM, and we are able to plot the linear elastic stress field of all our sample in a single graph, and we can find intersection point. As you can see, we can identify with, of course, with some uncertainty, there is a kind of range of critical distance and also of inherent material strength. Now, by using the values obtained here, we can see the maximum value of the fracture toughness and the minimum value of the fracture toughness here in this picture, with the average value of 0.98 megapascal square meter. These, as we're going to see in the next slide, are very good results, and they're in agreement with the bulk counterpart and also with accurate tests made at very small scales. Here you can see a comparison with data available in the literature. We have here samples of different orientation, all pre-cracked. On the left side, you can see that experimental tests do not agree with our results. However, in that case, the crack tip had a small finite radius, and as you can see, the fracture toughness values are pretty high. On the right side, instead, you can see experimental tests that employed pre-cracked samples. So we had accurate crack tip, and as you can see, our results are in very good agreement with those with accurate geometry. However, let me underline that when realizing pre-cracked sample, the procedure is much more complex, much more time consuming, and you need a larger number of samples to obtain a very reliable results. In our case, instead, by employing the theory of critical distances, we actually just use 4 samples, and you can see the results are pretty accurate. Moreover, you can see a comparison with the bulk counterpart, so the large scale fracture toughness of the silicon, and as you can see, this agrees very well with our experimental results and with those that employed accurate crack tips. So this means that the fracture toughness of single crystal silicon is actually scale independent. We can try now to understand why theory critical distances work so well. However, we have to involve more complex analysis, including the atomic level. We will not have time to discuss this in detail in this presentation, but I will try to give you a very brief overview, and I reported also several references. So we actually simulated fracture of cracked sample of plate made of atoms, and among the most important results, we identified 2 important quantities: the fracture process zone. This has been done in terms of displacement, but also with strain energy density. There are all the references below. And we also found the so-called K dominant region, that is the length on the singular stress field. So we found that the fracture process zone is always constant, regardless of the size involved, while the K dominant region tends to become smaller as the size of the sample decreases. Now, as you can see, both these quantities are very close to the critical distance identified before, especially if you would focus on L/2 and the fracture process zone. So I believe that the theoretic distances, being a length scale based approach, is able actually to capture the scale at which micro or nano mechanism of fracture occurs. And so it can give us also interesting information on those aspects. There is much more to say at the light of this kind of analysis, but for the sake of brevity, I just reported below the references. Maybe it's something we can discuss during the discussion phase. Here, the conclusion of my talk. It is very important to realize an effective crack tip, otherwise, even if treated as a crack, the result is that we don't have the correct fracture toughness. Despite the advancement in the fabrication processes, the manipulation and fabrication of an effective crack at this small scale is still difficult and very problematic. With the TCD instead, we don't have any more this necessity to realize an effective cracks. We do not worry about final geometry, we just need few random notches and we have a reliable fracture toughness. So this is an enormous improvement. The TCD can also give us important information on the magnitude of the fracture process zone. Being a length-based approach, I think that is able to catch the scale at which micro or nanomechanism of fracture are occurring. I think that TCD has an enormous potential when it comes to these new kind of applications, so hopefully we're going to see more and more applications, at least in the field of mechanical characterization or for example in the static assessment. Thank you for your attention.